Hello, good evening. This is Professor Khan, and welcome to Combustion Control Circuit EST-101. This is a continuation of theory and control, and in this course, we will kind of follow up with the control systems, electronically control system that is used for gas and oil burners in an industrial and residential uh, capacity. And so the first portion of this course, we will touch base on the basic controls for gas and oil and some components that allow us to do inputs and outputs. And we'll go further into industrial controls and you'll see how it's very similar to residential controls. And the last 3 or 4 weeks of this course, I will try to guide you through how to study for the Massachusetts Oil Burner Technician license. Okay, so let's start with a review for electrical circuits and basically the stuff that we did last semester and what did we learn and what are the things that you have to take with you into this semesters. Okay, let's go. And please check the Blackboard material for references along with this video. Okay, let's go. So we will review Ohm's law. We'll do a review of power law. I hope you remember both of these laws and they're not that complicated. Parallel and series circuit and how do we calculate all amperage, voltage, resistance, and power for parallel and series circuit. What is the difference between amperage, voltage, and resistance? Basic safety in oil burner techniques, and electrical component that we will go over while we go along and try to achieve the maximum amount of automation in oil and gas burners. We'll talk also about magnetism. It will stay with us for a while because we do move a lot of stuff using magnetism in terms of induction. We will do use motors and solenoids as well. Okay, so again, going back to the basics, what is energy? Energy is the ability to do work. It transforms from one form to another. It gives us the ability to move things, to heat, to activate, and electricity is one form of energy. We said that energy does not vanish and does not come from nothing. It transforms from one form to another, from material to energy, going back to material and to waves. They are all description of energy. It's a broad definition, but for us now we're dealing with electrical energy and we are transforming electrical energy to mechanical or thermal. So what is electricity? Electricity is the movement of electrons from one element to another, and it's a flow of electrons, so that's electricity. And this is an electrical circuit. It's a tool for us to be able to use electrical energy. If you put water in this system, it's not going to work. If you move wind through the system, it's not going to work. The only thing that will make the system move is electricity. So this is a way of us to utilize the energy in electricity. Similar to the water circuit, that a water circuit that have a faucet, have a drain, have maybe a turbine. If you don't have running water, you cannot utilize that energy. Similar to the wind turbine. If there is no wind, there is no use for the wind turbine. So wind has some energy, so we try to transfer the energy from the wind to the turbine. So you always have a medium to use this energy. Another example, your car is a system that can use the energy in fuel to transfer that energy into movement. So if you think about that concept, the electrical circuit is a mean or a tool for you to use electricity, the energy in electricity. Okay, hope this is clear. Moving on, this is our electrical circuit basics, which is Ohm's law. Voltage equals amperage times resistance. So we did a lot of examples about that. And if we look here, let's see, let me get my pen. So we have our voltage in the top. No, I want a free form. Our voltage in the top, resistance and amperage, and we said that voltage equals amperage times resistance. Uh, this is basically Ohm's law. If I said what is Ohm's law, you can say that and you will be all set. If you want to be more technical about it, you'll say it's the energy required to move one charge of electrons through 1 ohm resistance. But this will suffice for now. Erase and take this out. Okay, that's Ohm's law. The next is going to be power law, which is a sequence for that. We use power law to calculate the power consumption of that energy. So power always is the how fast do we spend energy, and we gave the example of horsepower in the car with high horsepower, it spends more gas than low horsepower, and we care about that because at the end this is how we spend electrical power, and this is what we pay for. In average there is 10 I mean 0.1 I mean 10 cents per kilowatt hour at least. It's not 1 cent, this is actually 10 cents per kilowatt hour. So we pay for electrical energy, and it's important for us to know how are we spending it. In a circuit in series, these are the things that again, all this we did go over already. The resistance adds up, and the current, let me get the pen, current remain the same. Does it? Yes, remain the same, and voltage drops and get used completely. What is the advantages of a circuit in series is safety. If one of the components fails, all of them fail because we have component going in series. So this is 3 light bulbs in series. If one of them fail, all of them fail. So we know that from the beginning. So this is a good safety control. You put switches in series, so if one of them activated, the whole circuit comes down. So it's used for safety and control. We know that. The disadvantage is that there is no backup. And if you are going to add loads in series, then you're going to have high load, which is not recommended. So for loads, you want to connect loads in parallel. And for switches, controls, safety, you want to connect them in series. Circuit in parallel, as you can see, the resistance drops. The more resistance we add, the more the total become less. You can see from this equation, it gives you a lot of redundancy and gives you a lower load for each resistance. Fuses and circuit breakers are used for safety. 15 amps is the oil burner control system. So when you try to install an oil burner, it should be on a circuit breaker that has 15 amps on it. 15 amps require 14 gauge wire, so it's good to remember those things. The circuit breaker for most controls in a circuit in a house residentially should be 15 amps. Reasons for that: short circuits and excess amperage draw. So the reason for having fuses and circuit breakers is they protect you against short circuits. And also, if you have excess amperage draw, how would you have excess amperage draw? That's if you have a fault in the circuit, and that's also for having a short circuit. If you think about short circuits for a small little period of time now, if you have 3 resistances in parallel, one of them drops out. What happened to the resistance here? It will increase. If the resistance increase, going back to Ohm's law, if the resistance increase and the voltage is going to be the same because we're supplying the same voltage, what happened to the amperage? It will decrease to keep the voltage the same. So a short circuit can cause you to have fluctuation in the amperage, and that can also be an alarm for you to deactivate the circuit. You can also have a ground system in the circuit breaker to alarm you if there's any short circuits or any circuit that got grounded, meaning that instead of touching the neutral, it's touching the ground. We also have thermal switches that get activated by heat. Okay, this is all supposed to be a review. Okay, introduction to electromagnetism. Why we did spend a lot of time talking about solenoids and motors and the motor principle and the relationship between magnetism and mechanical energy. And there's a video on our video here on YouTube that actually I will embed into the Blackboard because I think it's very important. It's 50 minutes into and it's divided to 10-minute segments. But I love the approach and how they try to make you understand the relationship between magnetism and electricity because it is the main principle for moving things using electricity, especially now that a lot of things are moving toward having electrical energy movement. There's a lot of electrical cars, a lot of wind turbines, so their interaction is becoming more visible for the end user. So check it out to kind of get a concept of the relationship between electricity and magnetism. So some of the most equipment we will be using is solenoid valves, motors, relays, and transformers. All these use the characteristic of induction. We use induction to move a valve, induction to move a motor, relays, transformers, and so on. We'll go over them little by little. They all use magnetism, which basically moving poles north and south to induce electrical current and induce movement in magnet. Remember when we used to play with toys and we have north and they will push each other? The same principle get evolved over time to produce electricity and also to do movement. So what is the left-hand rule for electromagnetic field? What does that mean? That if you put your left hand around the magnetic field, the thumb will point north. This just that's something you'll find from the video. What happens if you switch the current direction? The magnet will switch as well. And what is the left hand for coil? Is actually for coil, you wrap your fingers around the coil, the direction of the current going in the coil, and this going to the north will point to your thumb as the north direction. Check those left-hand rules for magnetism in the video. They're helpful because at some point you would love to know what is the movement of a solenoid if you activate it, and if you switch the current, should it be moving left or right. Okay, let's move on. So again, solenoid. If you look at solenoid valve, where are we going to see solenoid valves? There's plenty of those in your car. They are in the AC. They are in electrical valves and motors. So what happens here is we have a solenoid over this area that get deactivated and pulls this pin out. So in this situation, the polarity is very important, but here we're using AC current, so polarity is not the same. But if you're using DC current, that will be important because some of those are reversible as well. But for solenoid valves, it's only activated or deactivated. So when it's activated, the magnet is engaged and it will pull the pin up, and that will allow the valve to open. You'll see that in oil burners to allow the oil to go through the pump, and it's also in the gas vacuum. When you turn on your gas heater or gas burner, there's a solenoid that will open the airflow, and you can hear it. And once the airflow is achieved and there is no vacuum, the burner will start. So solenoid valves are all around us, and it's good to understand how they work. Also, if you have a hot water system and you want to have zones, probably you have a zone valve for each room. Okay. Motors. We'll work a lot with motors. We did spend 2 weeks last week talking about motors and their components, and they vary from sizes and shapes, from very large to very small, DC and AC, brushless and non-brush. So a few will work with a few motors in the field, and it's important to know how to distinguish one from the other. They are rated by RPM and horsepower, and they do a lot of rotating work. So they will work fans, they will work pumps, and they will work also compressors. So You'll be very familiar with motors and how to change those and what are the differences between them. This is how motors work. This is just an illustration of how there's an interaction between induction and rotation. Relays, again, we said relays are composed of contacts. These are the contacts here, armature, and coil. You'll always see the coil, and the coil is activated. Once the coil is activated, it's going to pull or push this lever here, and it will control the connection between those 2 or 3 pins. So this is the component of a contact. We will have a lot of contacts, and it's very important to know how they work, and this is what it looks like in real life. Some of them are clear. We did learn how to test the contactor. We can test the coil for continuity, and we can test the contact as well. Hopefully you'll be able to do that in Energy System Lab 1. Transformer, they do a step up and step down for electricity. And again, the number of coils here, the loops, determine how much voltage we get. So 110 going to 220 based on the amount of coils. How many turns do you have? And it can go up to 10,000 volts, and that requires us to have, I think, 5,000 turns. Okay, let me pause here a second. So transformers, we will be using 2 types of transformers from, at least in oil burners. We will have an AC transformer that transforms 110 volts to 24 volts, and that to operate the control. Most controls are operating at 24 volts, and you would like controls to be low voltage because they do interact with us in the living space. So you don't want high voltage there, and it's better for safety. We will have another kind of transformer that will transform electricity from 110 to 10,000 volts, and that's for ignition. But usually that's going to be in the equipment and not exposed to the user. Okay, moving on. Again, capacitors, that's something we have to learn about because we will be using those for motors. Bearings are part of the motors, and we have to be able to distinguish and know what's a running bearing and what's a malfunctioning bearing. Zone valves and electrical equipment testing. Okay, so capacitors, they come in different shapes and sizes. These are electronic sized capacitors. They hold a charge. Bigger capacitors actually are filled with oil, not with paper. This is actually special paper. This to show you what's inside a capacitor. So it looks like a car, like a battery in a way. They do transform AC to DC, and the unit is in farads. So again, capacitor is one of those units that hold the charge. So if you take a capacitor from a TV or from an AC, probably it's still a charge. Sometimes the charge decay with time, sometimes it doesn't. So always be safe and try to discharge the capacitor. And these are a lot of capacitors you see in electronics. They don't have that much charge. Zone valves, another mean of control. So zone valves, they control the flow for water or whatever heat transfer fluid you have for your system. Also, so we have a solenoid valve here that control the liquid flow. There are zone valves for air as well that open and close a damper. Electrical testing, this is an old-fashioned voltmeter pen. We did say there is an electronic pin or electric pin to detect voltage, and also there is something that we need to use for detecting amperage. So in the field, you need 3 types of multimeter, 3 types of meters. The voltmeter pin to detect the voltage presence, and a multimeter for detecting resistance or actually measuring resistance, capacitors, and temperature. And you need a clamp-on meter for amperage. So clamp-on meter is very important to measure amperage. This is a voltmeter by itself, a meter. So the clip-on meter, as you know, it's very important because it's the only way that you need to measure operating equipment amperage. Again, ohmmeter and voltmeter, they come together now, and they are a combination of 2 metering systems. Another thing I want, again, I'm just going over stuff we did last semester. These are common electrical symbols. It's good to know these symbols. If not, you can look them up, and they do vary from one field to another. So these, for example, like if you look at the ground, it's always the same. Resistance is always the same. What else? You see a lot of capacitors. Could be this, or it could be uh, this. Also could be a contactor, which looks like a capacitor. Again, a resistor. I've never seen this before. Fuse. It's a little bit common. Also, a circuit breaker looks the same way. So this is mainly for electronics. I think you can find another list in the book for other symbols. Unit conversion is very important. There are, again, this is just general information. There are 5 universal primary units, and everything else is driven from those primary units. So meters, seconds, uh, temperature, and kilogram for weight, and coulomb for charge. These are the 5 primary ones, and everything is driven from that. I just want to bring that to your attention if you ever wondered about that. Again, they have their equivalent in imperial system, and it's good to know the conversion between centimeter and inches, even though it's kind of a little bit far off. It's not straightforward, but if you're going to work with some foreign equipment or European equipment, probably they're going to be centimeters and meters. It's good to have this kind of conversion between watts, joules, and BTUs. A lot of the HVAC equipment trying to get away with I mean, get rid of the imperial system, but I think it's going to be here for a while. So it's good to know both conversion, or at least you can download an app so you can convert these back and forth. I'm not able to convert easily in my mind some of those units. I still have to go and resort to the app. But it's good to have this flexibility and not to be so rigid about one system or the other. Volume units, you need to know these because they will come in very frequently, and even in the HVAC field, they do change from one system to another and one equipment to another. So it's good to have these kind of conversions available and know where to look for these kind of conversions. Heat conversions. What else? Some prefixes. Those are very important. This is a conversion between Fahrenheit and Celsius. This is going to be important just for common knowledge. Some weights, and also some of these prefixes. They're very, very important, especially for micro, milli, centi, DC. I think that's what you need. Maybe kilo, mega, giga, and tera. But it's good to know what they mean, especially if you are going to do a lot of measurement. I mean, macro, you'll see microfarads a lot, so be aware of this symbol in here. Milli, you see that a lot. I don't think you see centi or DC that much, but you do see K for kilo or mega. Sometimes these are interchangeable. Sometimes mega means 1,000. I don't know why, but just double check the manual for each equipment you use and what they're referring to. Okay, so we'll kick off this semester using some electronic and some controls. So I'll still be using the Smith book for this week and the next week. And this is an introduction for Honeywell Control. What the approach I'm trying to get to you is we did all the basic electricity, and now is the time to use electrical controls. So in the beginning, we did make a lot of use of motors, contactors, switches, but as we relied more on electrical components, we start to find uses for to use controls and to take advantage of having a lot of things running by themselves. And one of the components, one of the things that you're going to be using for this semester repeatedly is the Honeywell CAD control. It's a very simple yet very sophisticated control. Uh, and this is a schematic for it. I hope you can look at it a little bit and try to understand what it means, and it's not very overwhelming. If you look inside the control, I mean, there is some schematic here. If you block this part here, you don't have to think about what's inside. But you look at the connection. There is an input coming from the thermostat. Let's talk about inputs. There's one input, thermostat. The other input is the CAD cell. So you have a terminal for the TT as an input and FF as another input. These are the inputs. Coming out of that control here, you will have a hot wire coming from the wall going to the black box. So this is power for the controller. It's not an input. It's going to be constant power. The orange wire here coming out, if you see, it connects to more than one components just to do simple controls based on the thermostat and the CAD. So it controls the burner, the oil valve, and the ignition. And lastly, in the white is basically the neutral coming from the components. So this schematic, even though it looks a little bit from the first look a little bit complicated, if you eliminate what's inside here and look at what's coming out of it, you can kind of get an understanding of where does it get connected. And we'll do a few hands-on connection for that to see how does it work. Okay, hopefully that makes sense. And let's see what else. I think that's it. I'll continue next week with more control. And uh, what I'm trying to, I will post also some other videos. I'll try to make them short. What I'm trying to get at is how are we going to use all these components and all those electronics that we get exposed to last semester uh, into the oil burner or a gas furnace to have automatically fully controlled system. All right, thank you, and I'll see you in the next video.